perfect. Okay, so 6.1 is all about kind of introducing our trigonometric equations, and so that's what we'd like to do here. So the first few examples are going to just involve a single trigonometric function, and in this case, we want to go out and solve for all values of x that would solve this equation. So we'll practice that first, and then we will kind of go back to solving either all solutions in the 0 to 360 range, or all values in 0 to 2 pi, which would be the radian solutions. So we'll work on both radian and degree solutions for these equations. So the equation we're working with is this one right here to start. It's 2 sine x minus 1 is equal to 0. So the first thing that we want to consider is just solving the equation for the trigonometric function. So that's what we'll try to start with, is our first technique. If we have a single trigonometric function, we want to isolate the sine of x in this case. So if I wanted to isolate sine of x, I would have 2 sine of x is equal to positive 1 if I add 1 to both sides. And then I can divide by 2 to get that the sine of x is equal to 1/2. And for this one, we will just solve this equation in degrees. Certainly the question itself on XYZ will designate if you want to go for degrees or a radian solution. So if it's a degree solution, we want to find values of x that are in between 0 and 360. This is how they'll be denoted if we want to have our solution in degrees. And then in the next problem, we'll take a look at the solutions in radians. Okay, so now we want to just consider what equation would solve, or what angle would solve this equation, sine of x is equal to 1/2. So
30 degrees.
What's that?
30 degrees, Mr. Copeland?
Yeah, 30 degrees would be one. That's excellent. So we have one angle that would be 30 degrees. Excellent.
And it'd have to be in the same position, right? On the unit circle.
Right, so that's one of the solutions to get sine equal to 1/2. What is another angle in the second quadrant that would do that as well? Because remember, the sine function is positive in both the first and the second quadrant. Not quite 135, Sorrel. Yeah,
150 degrees.
Yeah, 150. We could have that same reference angle here, 30 degrees. And so that second solution we could have here in the second quadrant would be 150. That would be correct. So there's two solutions for making the sine of x equal to 1/2. So those give us the kind of the principal angles in the first rotation of our unit circle. And now I want to consider, how would I find all possible solutions? Well, if I wanted all possible solutions, I want to get every coterminal angle to these two given angles. So let me write that down. So if we were going for all possible solutions, this is going to get all coterminal angles to, in this case, 30 degrees and 150 degrees. So 150 and 30 degrees would be our two solutions in that unit circle. And now if I wanted to do all possible solutions, I would write the solution set just like this. I would say would start at 30 degrees plus, since we want a coterminal angle to 360, or to 30, I would say, add 360 times a value k, where k is an integer. So we're going to be adding integer values of 360. So if I add 360, I'd get a coterminal angle. If I add 270, I'd get another one. If I subtract 360, I would get another coterminal angle that would be a solution. So that would be one set of possible solutions, where k is an integer. And then I would add to that, or at least a second set of solutions would be 150 plus 360 times k. Again, where k is an integer. So that would be the set of all possible solutions for this equation. All right, so let's pause here and just see if we can wrap our minds around what we've just done with that coterminal angle business. Is there any questions that I can answer with this set of solutions right here? So this kind of set right here.
Is k just a value for the number of times around a unit circle, basically?
Right, yeah. So it's an arbitrary number. It could be any integer, again, that it wants to be, but that would be the set of all possible solutions. So k could be, values -2, -1, 0, 1, 2, up to whatever you want it to be. So that would be just the set of all possible, just written in a closed form. Because there's unlimited number of coterminal angles to those first given angles. And so to write that, we'll just represent that with a k.
Great, thanks.
Mm-hmm. Any other questions before we tackle the next one in terms of radians?
Would the answer be like 150 degrees plus 360 degrees K?
Right, yep, that would be one part of it, and then the second part we'd want 30 plus 360 times K. So in the
Gotcha.
in the program, it'll have kind of spaces provided to write kind of those components.
Okay.
Mr. Copeland, so on the next example would be rad 3/2, and then it would be the degrees of 30 and 330, right? The next example?
We'll walk through that.
Oh, I'm sorry.
We'll walk through that. Is there any other questions with this first example, just getting introduced with this? Okay, so let's take a look at the second one, and again, we'll do this one in radians. And so when we want to do a problem in radian, what you will see on the program is we want solutions from 0 to 2 pi. So that would be the solution sets that we would usually get for the radians. So if you have a 0 to 2 pi range, that's indicating that they want the solutions in radians. So just make sure that you can make that distinction. And again, we'll go through all possible solutions.
Wait, how do you know if you want the radians?
Excuse me?
How do you know if you want the radians?
How do I know?
Yeah.
In this example, I'm just designating radians, but in the problems itself, you will see finding solutions from 0 to 2 pi. That's that indication for you in the question that it will be in radians.
Gotcha.
Yeah. So I don't have it in this notes, but that's what the program will indicate. Okay, so again, since this has a single trigonometric function, we're going to want to solve for, in this case, cosine. And then we're going to work to find two solutions in our first round of the unit circle, and then work with coterminal angles. Okay, so again, we could start with subtracting the square root of 3 from both sides and get 2 cosine of x is equal to negative root 3. And then here dividing by 2, so we want to do a cosine of x is equal to negative root 2, or root 3 over 2. Okay, so let's take a moment to think for a moment with this, and we'll do a little diagram again. Where are we going to find the cosine of x equal to the square root of 3 over 2? What would be some angles that would represent that?
150.
Okay, 150. And in this case, what is the radian calculation for 150?
5 pi over 6, 7 pi over
Okay, so we would have x is equal to 5 pi over 6. So that's a second quadrant where the sign is negative.
Mr. Kogan, if you don't mind me asking, why did you make it negative? Why did you not take away the 2 first? Because that's where I was leading off from the start. Like you did negative rad 3. Why didn't you go from 2 divide by 2 on the 2 cos x?
Why did I not get rid of the 2 first?
Yeah.
Just order of operations with solving the equation. We always want to do our subtraction first or addition, and then the last operation would be working with that 2.
Oh, okay. Okay.
It's just order of operations for solving. So really the reference here is going to be the pi over 6. And that first angle, we would have 5 pi over 6. What would be the second angle that we'd want to get for this solution?
7 pi over 6.
Okay, 7 pi over 6. So that same reference in the third quadrant, if we have a pi over 6 here, this blue angle coming around would certainly be 7 pi over 6. So that's the second solution. That looks great.
I'm so sorry. How did we get pi over 6 again? No, 5 pi over 6?
So this is the first angle in radians that gives us the cosine of negative square root 3 over 2.
Oh, okay. I see now.
Yeah. So those the quadrants 2 and 3 will give us a negative cosine, and that happens to be the angle that gives us the negative square root 3 over 2. So both of those will have the same cosine, or x coordinate on our graph. So we have the two solutions, that's 5 pi over 6 and 7 pi over 6. So that would be the two solutions in the range of 0 to 2 pi. But again, we want to go through all possible solutions. So if we wanted all possible solutions, what's the first way I could write all possible solutions with my first angle?
Would that be 5 pi over 6 plus 2 pi k?
Yep, plus 2 pi k. That's exactly right. And then how could I write the second portion of that solution?
be the 7 pi over 6 plus
Mhm.
2k, or 2 pi
Yep,
k.
excellent. Yep, 7 pi over 6 plus 2 pi k. Now the 2 pi is just going to be representing another rotation of that circle, and we'll be back to where we started. Excellent. So, and then again, k is an integer. So positive or negative whole number.
How do you know when you go farther, well, once you start using the 5 pi over k, or 5 pi over 6 plus 2k, how do you know when to stop?
How do I, so in terms of finding these angles or doing the coterminal stuff?
The coterminals, like, because I know for in 6.3 you need to do like an entire list. It's just like, how do you know when
So
to stop?
we'll get to that list. So here we're just looking at all possible solutions. So there's actually no necessarily like list of find your first 4 solutions. We'll get to those types of questions soon, where we need to just find the first 4 solutions. Yeah. So this is just asking, for a little bit more than just a short list of solutions. So we'll get to those type of questions as well. Okay, so those are our solutions in radians. Any questions with working with the radians on this one? Okay, so in a way, these first 2 were kind of nice. They worked with some side ratios that we were familiar with, and some common angles on our unit circle. This one we're going to have to work with looks a little bit different. So this third example, we still have kind of one trig function, but we see it in multiple places in our equation. And so let's highlight our equation here. That's what we're going to be solving. And notice that we want to find theta, where theta is between 0 and 2 pi. So again, this is designating that we are working in radians. So let's just note that. We're going to be working in radians. So let's kind of work with the equation a little bit first, and then we'll see that this is going to be solved in a little bit different fashion than the previous 2. So to start here, notice that we have some sine terms and some constant terms on both sides. So we'd like to kind of reorder those if we can. So to do that, I'm going to do a couple things right off the bat. We could just simply subtract 7 sine, get the sine on the left side. And so I have minus 4 sine of theta minus 2 equals -1. I can add those constants together by adding 2 on both sides. That would cancel. Again, I'm just going to be working to isolate the sine of theta on one side of the equation. And just about there. What's the last thing I could do here to isolate sine?
Distribute the negative.
Okay. Yeah, so in this case, we'd want to divide the negative on both sides. So -4, we divided by -4. We get our sine of theta. So here we have sine of theta equals 1 over -4. So this certainly is not a common ratio for us, but we can still go out and solve for our radian calculations. So we have the sine of theta is equal to -1/4. So let's take just a moment to picture this with a little sketch, and then we're going to actually use our calculators to approximate some angles for this. So again, we want to consider, where is the sine function going to be negative? Which two quadrants would give me a negative sign? Yep, 3 and 4. So let's take a look at 3 and 4. If I have a sample triangle here, the sign for that would be -1 and 4. We can also have that same triangle in the fourth quadrant. Not exactly the scale, but those two triangles would represent my angles. So I've got one in the third quadrant there in red that we want to go solve for. We'll call that maybe θ1. And go out and solve for that. And then we have a second angle. Let's call it in green. We have θ2. So two solutions at least in our first cycle of our unit circle. So I'd like to go out and solve for those two specific angles. Any questions so far? Everybody tracking with me through the picture? Okay. So now here's where we're going to diverge. Question? In the chat, Alyssa, how do we know which side is negative? Well, the function is going to determine that. So notice that we have a sine function. Oops, I want to go back to that. Notice that we have a sine function here of theta. So when I consider the angle, this reference angle, we'll call theta hat, we want that ratio for the opposite and the adjacent to be negative. So this is our opposite side. This is our hypotenuse. So that's going to be the determining factor. We want to use those sides. Instead of the adjacent side, we want the opposite and the hypotenuse to have that ratio. Okay. Any other questions before we get to the solving with our calculator here? Okay, so let's consider now how we're going to solve this one. It's a little bit different because these ratios here are not on our unit circle. So to do this, we are going to consider the following. Theta here, we're going to actually use a inverse function. To find the first solution for theta, we can say that theta itself is going to be equal to the sine inverse. We're going to be using the inverse function for sine, and as input, we're going to use that side ratio. Okay, and again, make sure that our calculators are in radians. That's really important. So do a double check here before we start and consider our calculator needs to be in radians. And then we're going to evaluate that sine inverse from -1/4. So if you guys have that, whenever you guys are able to punch that in, go ahead and drop your solution into the chat, and we'll just round to 4 decimals. So round to 4 decimals. Give you guys a moment to do that. Again, make sure that your calculator's in radians. All right, we've got a number collecting negative 0.2527. Okay, that's looking pretty good. I think that is going to be our solution if we round to 4 decimals. So let's write that down. So we have negative 0.2527. Okay, so now we want to just determine, well, which answer did we actually solve for in our picture? Because we want to have 2 here, and the calculator is only going to give us 1 solution. So the solution we actually grabbed was the 4th quadrant solution, and it represents it as a negative because remember that the sine function goes between negative pi over 2 to pi over 2. So it's going to give you solutions in the 1st and 4th quadrant, where that 4th quadrant has a negative solution. So if I consider, again, this angle is really angle 2, but it's the negative version. So this is negative 0.2527 sitting right, going in the negative direction. One way I can represent this solution as a positive, as the actual green angle that's wrapping around, is I can add 2 pi to this solution, and that will actually give me the green angle that's wrapping around into my 4th quadrant. So if you take exactly what's in your calculator here and just add 2 pi to this, go ahead and do that. And again, let's get our solution to 4 decimals. If we add 2 pi to that solution and get the positive version of that angle, what do we end up getting there? Excellent. Anya and Aiden, yep, Joseph, Sam, excellent. So here we go. So we're going to get 6.0305, and that's in radians. So that's our theta 2. In radians. All right, now I'm about solving for the theta 1, that original red angle that is the 2nd quadrant. How could I do that? How could I use reference angles here to help me out for that 2nd one? If I consider that red angle that's coming around, and I'm just going to use the picture for right now, I know that if I go all the way around to this point, this is pi units, and let me use actually red to distinguish from the work that I'm doing on the 2nd one. So going around the circle halfway is pi units, and then I'm going an additional, we'll call it that theta hat right here. That additional little space that I'm going into the 3rd quadrant, we know a reference angle for that, and that happens to be 0.2527. That's the distance here that goes just right there, that extra bit. So exactly, yeah, we're going to want to just add pi and that reference angle again. So if I wanted to get theta 1, I'll just do the work over here, theta 1, take that reference, and it'll be positive in this case. because I'm adding an additional 0.2527 to just pi. So if I do that calculation, what do I end up getting with our 4 decimal solution? Okay, Anya's got 1. See if we can confirm that same solution. $3.3943, and that's readings.
Professor, why is that reference angle positive instead of negative in this one?
Well, we know it's the same, so we're going in the positive direction this time. Notice that we're going from, we're going in the counterclockwise direction. And so that angle right here that I'm going to draw over again, we are kind of thinking about, again, that red angle is going, or yeah, the red angle is going in the counterclockwise direction. So whenever we're going in that direction, that additional piece is always going to be positive. But it's the same
Okay.
distance from the other reference angle. So as long as we're going in the counterclockwise direction, we're always going to be adding those components together. All right, and let's jot that down. Question?
So treat the red theta hat as like the antithesis of the black theta hat? Or green, or whatever you want to call it?
Yeah, so the green, the reference angle that we got was negative because just the sine inverse function always comes out with a negative solution in that third or the fourth quadrant. And so we were just simply creating a positive coterminal angle that represent that angle in the fourth quadrant. But that reference angle is still the same in both positions.
Why are you adding in the first solution 2 pi, but in the second pi?
Because we're in a different quadrant. So if I'm in the fourth quadrant, if I wanted to get my angle there, and I'm starting with, again, this negative angle, to get a coterminal angle to that, I'm just going to get 2 pi, add 2 pi, because really I'm just finding a coterminal angle in that first solution. In the second solution, I'm just going to be adding 2 components together to get to the third quadrant.
Okay,
so there's
thank
kind
you.
of, yeah, 2 different calculations going on. But it's really determined by the quadrant. Okay, so I think we have actually solved this question. These are our 2 solutions between 0 and 2 pi. So I'm going to box these solutions. These are one, oops, we want to go away with. And there we go. Any other questions from this work right here using the inverse function?
So let's say if you have an equation that somehow has one in the second quadrant and one in the fourth quadrant, would the theta hat be also positive in the second quadrant?
Yeah, so let me.
Sorry, I'm just trying to like figure it out.
Well, yeah,
because I know some are like that.
So if you, let's see. Well, if you're going to do a fourth and a So that would be really a negative tangent. So if there was something like tangent of theta equals, like, say, -1/2 or something, that would be a case where we'd have solutions in the second and the fourth quadrant, just for more something more specific. If we had a reference angle, we're going to get a reference in this case. Say the references, say, we'll do degrees this time just to highlight. Maybe it was, -22 degrees or something was the calculation you got from your calculator. If that was the case, we'd again want to just find in the fourth quadrant angle that actually wraps around. So that would be 360 and then plus -22 to get that solution. Call that theta1. So that would give me the coterminal angle that goes in the counterclockwise direction. And then to find the theta2, that theta2 would have that same reference angle in the second quadrant. So that would have kind of this 22-degree angle sitting right here. And so to solve for that angle, in that case, in the second quadrant, we'd want to just do pi minus that reference angle to get to the blue angle in the second quadrant. Because we don't want the full pi units, we want 22 degrees less than that pi unit.
Okay.
I know it's, yeah. Actually, in this
I was just
case,
trying
it
to
would
figure
be,
that out.
sorry, it would be 180 in this case, just to be consistent here. 180 degrees. It would be 180. And I just made those numbers up, but that's at least the thought process you would go through if that was the case.
Okay, thank you. I was just like trying to figure it out, and like, so I was just trying to figure out if everything in like the second or first, if anything in the fourth quadrant would affect cause the opposite to happen to any other quadrants,
Yeah.
i.e. the positive to the negative.
Mm-hmm.
Okay, I was just trying to figure it out because it's like you had the 2 right there, and it's just like it makes sense kind of. But if you did it another, say it was 1 above that, I was wondering if it would still act the same.
Gotcha. All right. So, other questions before we jump into the next kind of tier of equations? Okay, so next one we're going to do involves a quadratic of trig functions. And to just start us off, I'm going to just go back to a little bit of algebra in terms of how do we factor polynomials. And specifically, here we're going to be factoring a trinomial. I wanted to solve this function here for x. I would want to consider, again, setting this quadratic equal to 0, and then see if we either can factor or use the quadratic formula if I was to do this. So we're kind of going back to a little bit of algebra techniques here. So if I wanted to set this equal to 0, first, I'd subtract 5 on both sides, just have a 0 on the right. Now, if I wanted to consider thinking about whether this factors or not into kind of a binomial pair, well, there's a couple things to consider when we think about factoring here. Get back to where I started. apologize for the there we go. So I want to consider a couple things. First, we are going to consider that first term there, 2x squared. So we do need a combination that's going to multiply to that in the front. So we could say that 2 times x and then x would work for those first two positions to multiply to 2x squared. And then I'm going to look to -5. So I want two numbers that would multiply to -5. So there's really only two combinations there that would work. I could either have -5 times 1 or 5 times -1. And so we can either go through, there is kind of more technical process to factor these, or we could just consider kind of a guess and check method here of figuring out what combination of -5 and 1 that we want. In this case, to make this factoring work, we'd actually need the +1 and the -5 to factor like that. To double check that this is the correct factoring, we use that middle term. If I looked at the cross terms here, when I would multiply this out, I have just an x. And then the second cross term, multiplying these two, I would have -10.
So we're using FOIL?
So we're kind of factoring, which is kind of the opposite of foiling. So foiling would be, I guess, what we're doing here to check, I guess. Yeah, you're right. So we're just kind of trying to multiply those cross terms. What I want to double check is this cross term matches up with the addition of those two cross terms. And I think it does here. So x and then -10x give me -9x. So that's kind of where we would double check that we have the right factoring. But again, this is just a little bit of review for algebra. If you have a technique that you like to go to do factoring, by all means, grab that technique. So anyway, we have our factoring here, and we would go out and solve the rest by, again, setting each of these components equal to 0. Now, I'm going to try to actually go down to the trig problem that's very similar to this at this point, and just relate kind of this algebra technique that we just used with the next problem. So I'll try to keep this in view for just a minute. So notice that the actual trig problem that we're going to be working on below, we have 2 squared t minus 9 5. This is really similar, except the only thing that changed is x here is cosine t. So in this case, x is equal to cosine t. So we're going to be working with this quadratic in terms of a cosine function. So just like we factored the regular quadratic function on the top problem, we can still do that same factoring on the bottom, but now use a cosine t in terms of the x. So whenever we see something like this, we can, again, consider setting that equal to 0. We'd have that same format. That equals 0. And we would factor this, but now we can factor in terms of cosine. And so it would look like this. We'd have a 2. Instead of x, we'd have 2 cosine t plus 1 and a cosine t minus 5. So it looks really similar to that previous factoring just in terms of x, but now in terms of x, we have the cosine t. So one technique that you can kind of use as well is if you have this trig function in terms of your quadratic, you is throw in a substitution variable, call it x, and just rewrite this as 2x squared minus 9x equals 5, and then work the problem from there. And then use your substitution later. It is a little bit extra work to do the substitution, but I just wanted to show you here that we can factor this just like we did with the original quadratic in terms of x. All right, so let me pause here before we actually complete the solve. Is there any questions I can answer with this quadratic form? Now we're going to just, again, consider just like a regular quadratic. If I have it in this factored form, I'm going to want to consider setting both of these factors equal to 0 and see where this leads us. So we'll start with the first side. We have 2 cosine t plus 1 is equal to 0. We'd like to go out and solve for t, again, where t is between 0 and 2 pi. So let's consider that one. We're going to set, again, the cosine t equal to some constant. So we have 2 cosine t negative 1, or cosine t is equal to negative 1/2. Okay, so let's consider now, where would we find an angle that gives us a cosine of negative 1/2? Where would that angle be?
Could 240 be an angle, Mr. Krogman?
So 240, so we're having, yep, we're going to definitely be in the third quadrant.
And then 120, 120.
So yeah, so we're going to have a second quadrant angle for the cosine being negative. And I think that would be 120. What would be the radian solution for that?
So 2 pi over 3 for 120, and then for 2
pi.
Yeah.
So we'd have okay. And where would we find another solution?
4 pi over 3 for 240.
4 pi over 3, right? So having that same reference angle, we did that. Let me go with this guy. Reference angle wrapping around here would be 4 pi over 3. So 120 would be one of those, and then we'd have 240 for the other one. So that's really 240 or 4 pi over 3. Okay, looks good. So we have two solutions for that side of the equation. They give us the cosine equal to negative 1/2. Let's consider the second side of this equation. This will be a little bit quicker. If I set cosine of t minus 5 equal to 0, I say that equivalently cosine of t equals 5. Is there any solutions that I could grab for this side of the equation? Is it possible for the cosine of t to be equal to 5? Okay, Sam says no. What is the restriction for cosine? where would we find solutions for cosine? Yep, exactly. So any values here, that's certainly where the angles would be we're looking for, but the cosine function ranges from -1 to 1. So the actual solutions that we find for any cosine of any angle maximize at 1 and minimize at -1. So if we consider the graphs of our cosine function, remember that we start at a +1, and our minimum is at -1 for a regular cosine function. So we cannot get a 5 out of any cosine t function here. So this would do no solutions. No solutions. So the only solutions we will get, again, will be those two solutions, 2 pi over 3 and 4 pi over 3 will be the solutions for that. Watch it for those scenarios where we have no solutions for one of the factors in our quadratic.
So doesn't the unit circle also have like the points of like 0 being 1 being the cosine, 0 being sine, and then goes through it sorry, brain's kind of flutter-brained right now. Tad tired. So it'd be 1 0 0 1 -1 0 0 -1 and back to 1 0 again. So definitely no 5 in that
Right.
possibility at
Yeah.
all.
Yep, so the north, south, east, west directions are where the cosine and sine are maximized and minimized. So it's certainly going to be outside that range. All right, any other questions before we go to one application and then we'll take our break? Okay, so let's consider an application we can now work with using some projectile objects. So if a projectile such as a bullet is fired in the air with a initial velocity v, at an angle of elevation theta, then the height h of the projectile at time t is given by the equation h is equal to -16t squared plus vt times sine of theta. So if we, to find the angle of elevation theta of a rifle barrel, if a bullet fired at 1400 feet per second takes 2 seconds to reach a height of 850 feet. Give your answer in the nearest tenth of a degree. So we want to have our calculator in terms of degrees. So that's our first thing, at least we can change in our calculator. Is I want to go to nearest tenth of a degree for that calculation. Okay, so let's consider how we can fill in this formula to solve for our needed quantity. So do we know the height? What would that height be that we reach?
850 feet.
Okay, we have 850 feet. And we'll have -16 t squared. So the time that it took us to get to 850 feet was what? How many seconds did it take? 2. So we have 2 seconds. That's our t. This is our h. So we'll have 2 squared plus The last thing we would need is the velocity. So that's our velocity, 1,400 feet per second. And times t again, so we'll want to have that 2 one more time. And sine of theta. We want to find that angle of elevation of the barrel. So in terms of our angle of elevation, we know the angle of elevation here we're going to be searching for is going to be some acute angle for that angle of elevation. All right, so now we're going to do a little bit of algebra, see if we can solve for this theta angle. So we'll just do a little bit of condensing of this equation. So we have 850 is equal to negative 16 times 2 squared. What would be that calculation give us in that first term? Negative 64, yep. And then plus 2,800 sine of theta. If we add 64 to both sides to balance the equation, we get that negative, and we have 914 is equal to 2,800 sine. What would we do next in this process?
Divide.
Divide by what number?
I think by 900. I think like 208. 2,800.
Yep. Divide by 2,800. And here, I would recommend just keeping it like this fraction because we can work with it just like this. So we know that sine of theta is equal to this ratio right here. So don't worry about reducing this or putting it into a decimal. Just leave it just like this ratio. And how would I go out and solve for theta at this moment here? What function would I use? I have sine of theta is equal to this ratio. How would I get theta back?
So just the inverse of that ratio, inverse sine ratio.
Yeah, I could take the sine inverse of that same ratio. I'm just going to keep that ratio collective just like it is. I'm not going to change it or reduce it. I don't need to do that. So I'm just going to put exactly that ratio into the sine inverse, and then we're going to see what we get. Again, make sure our calculator is in degrees, and we will round to the nearest tenth of a degree. So try that in your calculator, see if we can get a common solution. Got a couple solutions rolling in here. Sam and Anya, Joseph, nice.
I got a question. During the final, let's say we made a rounding mistake. Like, let's say we didn't round. Would that count off?
So if you
Like on the
so if you
calculator it
put
says
more,
19.05, and let's say I put 19.05 on the final, but I still rounded it to 1.
yeah. So I wouldn't take all your points because you have the work, to have that solution. It would probably be just a pretty minimal markdown in that case, just for not seeing the directions. Yeah. So it might be like a half point or something.
Gotcha.
Yeah. All right. Looks like we've got at least 3 of you guys with the correct solution, 19.1 degrees. I think that would be our angle of elevation. So again, this is what we'd find for that angle of elevation of the the rifle. Super. All right, so is there any questions with this solution here? A little practice with the inverse function again.
So basically, it'll tell you if it wants it in the degrees form or the radians form, I think.
Yep, every question will tell you which form it wants to be in. Sometimes it's not going to say degrees or radians. Sometimes it'll say, you know, this expression right here. So that would tell us that we're in radians. So it will tell you and designate that either with saying radians or degrees, like that last problem, or just putting the range of values that they want the angle in.
So it just, but what I meant was like for the calculator when you're plugging it in. Because for the previous ones, we needed to put it in as a radian to get our answer, and then but this one you had to do degrees.
Right. So you want your calculator in degree mode for this last one, and it'll spit out a degree solution from that inverse function.
Okay.
Yeah.
But how do you know if it's a you need to put it in certain code? I just don't want to make a mistake in the final and go like I use
yeah.
the
So
degrees one instead of
if you're designating, it says obviously this one you'd want it in degrees because it wants the answer in degrees. So when you do that sine inverse function, this can either give you a radian solution or a degree solution depending on what mode you're in. So you want to definitely match the mode to what type of solution they want.
Okay.
So okay, so I think this is a good time for a break before we jump into next section 6.2. So we'll take a looks like 7-minute break. We'll start back up again at 9:10 here. Back up at 9:10, and I'll see you guys in a little bit. Excellent. So this next section, we are going to work with some more trigonometric functions, which have multiple trig functions in a single equation. So this is going to use some of the kind of identities work that you guys were working on in chapter 5. So we'll be kind of doing a little bit of a review of those things as we go in this section. So let's begin with question A. We're going to start with the 4 sine of theta minus 2 cosecant of theta equals 0. And we're going to be looking for solutions in terms of roots. So we're going to want to have our calculator in radians for this section. All right, so let's consider first how we might want to tackle this problem. We have a secant and our cosecant and a sine function. So how would we represent the cosecant in a more simple way in terms of sines and cosines? How would we be able to represent cosecant? Yeah, that's 1 over sine. Excellent. Yeah. So we could think about starting with, this is 4 times the sine of theta, and then minus 2, we could say 2 divided by the sine of theta equals 0. Okay, so if we take the reciprocal, it's really 1 over sine of theta. We could make that 2 over the sine of theta, since we do have a 2 as a coefficient there. All right. Another thing we can maybe notice here is that we can factor out a power of 2 in this equation. So that might be helpful as well to factor out a power of 2. So we could say that 2 times 2 sine of theta equal to minus 1 over sine of theta equal to 0. So we do have things in terms of sine, but we're not quite ready to necessarily put it all together yet. What would be another thing that we could do to start to simplify that expression on the left side? Any simplifying steps that we could make?
You'd simplify out one of the signs.
Okay, so simplifying one of the signs, what did you have in mind?
Like cross cancel, 2 sine
Yeah.
and negative sign.
So we can't quite necessarily cross cancel since we're not doing multiplication. Let's see, Kevin, you said multiply by a sign. I think that's sounds like a good idea. So in terms of, we could consider multiplying by a sign or considering just getting a common denominator to combine these two. So that's kind of the same idea, but we could say if we wanted to multiply by a sine theta over a sine of theta, that would make that sine squared theta to get a common denominator of sine, and we could add these two together. So that would be an appropriate operation we could do. So we could rewrite this as 2 times, looks like we have a common denominator, so we could say that this is 2 sine squared theta minus 1, and then divide by just a sine theta. And that's to 0 still. Okay, so now that we have this format set equal to 0, now we can consider actually thinking about the numerator here. If this whole fraction here is equal to 0, that would force the numerator itself to be equal to 0. So we could say that 2 sine squared theta minus 1 has to be equal to 0. The only catch here is we want to make sure when we get our solutions that sine of theta is not equal to 0. Okay, because if the sine of theta is equal to 0, then we're going to have problems in this equation. So this is one check that we're going to need to make at the very end, is making sure that the sine of theta, whatever angles we find, is not equal to 0, because that would make this fraction on the left side undefined. So we want to stay away from that for sure. But we can determine that to solve this, we just want to set that numerator equal to 0, and that will make that full fraction equal to 0. Okay. Is there any questions from taking that logical leap? That numerator itself has to be equal to 0?
Okay, can you explain to me how you get the sine squared part? I knew you had a general idea of like multiplying the sign, but did you like?
So we really, so we multiplied sine theta over sine theta to the existing 2 sine theta.
Okay.
So we just put a sine theta in the denominator and squared the 1 in the top.
Okay, I just wanted to make sure because I'll probably look back at my notes and go, "What the heck just happened?"
Okay. All right, so now we're going to be working with equation here. 2 sine theta equal minus 1 equals 0. So let's consider this next step. We now want to just isolate the sine squared theta. So I'm going to add 1 to both sides. And then we could divide by 2. We get sine squared theta is equal to 1/2. Now, if I wanted to get sine squared theta, or at least get sine theta out of this, what operation should I be using to get my sine theta? How can I, in other words, get rid of the squared power there?
Square root.
Yep, we could just take a square root of both sides to get the sine. So we get sine of theta is equal to, here we'll have a plus and minus, and we'll have the square root of 1/2. If we considered how this would actually rationalize, we've seen this fraction before. Couple ways we could rewrite that is plus or minus 1 over the root 2. Or we've seen this also represented as plus or minus square root of 2 over 2. So this is a common ratio that we have seen in the past, square root 2 over 2. So we really have sine of theta equal to plus or minus square root 2 over 2. Well, let's consider maybe just the positive version of that root. If I were to determine where the sine is equal to positive root 2 over 2, what angle would I be given there? Or would my sine be equal to square root 2 over 2? Yep, pi over 4. Excellent. So that would be a 45-degree angle, or pi over 4. Get a pi over 4 angle. And since that we want both the positive and the negative solutions at this ratio, we can consider there's really going to be 4 angles all the way around, 4 solutions, and they're all going to be at 45-degree angles in the given quadrants, or all 4 quadrants here. So we can make really 4 solutions here into each of these quadrants. So the first solution in that first quadrant in red is pi over 4. What would be our green angle solution here? Yep, that is 3 pi over 4. Excellent. How about the purple? That is, yep, 5 pi over 4. We're just adding another couple 4 pi. So this is 5 pi over 4. And that's pi. So I'm just adding another 4th to that pi. And then finally, the 4th quadrant solution, black, we could say that's going to be 7 pi over 4. So it's 1/4 of a pi less than 2 pi. So we have 4 solutions there for the equation. And just to double check here, none of those 4 solutions force sine function to be equal to 0. So that is a good check. That's not happening. And so all 4 of these solutions can be valid. And so we'll just leave those 4 solutions out of the solutions here. So we have theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. We have 4 solutions for that set. And again, we can stop because we're only going to be finding solutions from 0 to 2 pi. So we don't need any coterminal angles to these. We're just looking at the first rotation of our unit circle. All right. Is there any questions for me that I can answer for part A?
Okay, so I always have trouble with the second quarter because it's like the other ones are easy to figure out because it's just like just add pi to whatever your first answer was. For the third quadrant and the fourth quadrant is just subtract or no, not subtract. Wait, yes, subtract. Well, it's 2 pi subtract by your original quotation to get your. But your second one, how exactly do you do that? Do you just add the two? Like add 2?
Yeah, I mean,
Or
another
pi
way
over 2?
you could, yeah, so you get, well, yeah, this is a good example because they're smaller numbers. So to get that second quadrant solution, you're really getting pi minus pi over 4. So your original solution subtracted from pi gives you 3 pi over 4.
Okay, thank you. I was just like, I always use the other ones. I'm like, wait, how do I?
Yeah. So you're
Square
subtracting
pi
your
is kind of a
reference
hard
angle
one to
for
deal
pi.
with. Thank you. This is like my brain farted for a minute.
Can I ask you an unrelated question?
Sure, yeah. That's right.
On chapter 3 test, where is the chap? No, I'm sorry. What's the chapter on the unit 3 test?
So the chapters there are going to be 5 and 6.
Gotcha. Okay.
So the identities and then the equations. All right. So let's take a look. The next one we're going to do involves a double angle formula. So we're going to kind of review how to work with double angles, and hopefully we can recall that with us. So we have a sine 2 theta minus cosine theta equals 0. So if we think back to chapter 5, what's the representation that we would give sine 2 theta? We're looking at, and you can, for now, you can reference, there's that identities page that has this as well. If you're working with that during your homework. How do we represent sine 2 theta? Yep, 2 sine cosine, right. So we'd have 2 sine theta cosine theta. And then we'll have the subtracting cosine. Okay, so excellent. So we can use that identity to help us with the this specific equation. What do we see as something we can do to simplify this equation further after using that identity? Any operations that I could use? Do we have any common terms on the left side that might be helpful for us? So I can't necessarily subtract right away. If you notice, we do have 2 cosine functions here. So the cosine and the cosine.
So just divide the 2 cosines?
Yeah, divide or just factor them out. Yeah, so that would be a form of division, but we can't necessarily get rid of them completely. So we can factor them out as a cosine theta and then leave behind 2 sine theta minus 1. So that would preserve the left side of the equation, but just kind of separate our sines and cosines out. So we have that left side kind of in factored form. Now we can look at kind of two different equations to solve. One would involve the cosine theta equal to 0, and the other would be 2 sine theta minus 1 equal to 0. So let's start with the one on the left. What angle would give us a cosine equal to 0? Where do I find cosine equal to 0? Cosine, again, is our x-coordinate. So if we considered our unit circle where we have an x-coordinate of 0.
Is that pi halves and
Yep.
3 pi?
So, yep, pi half will give us a x-coordinate of 0 and 3 pi halves. Okay, excellent. So that would be two solutions. Excellent. And now let's turn our attention to the other side. 2 sine theta minus 1 equals 0. If I rearrange this first for sine, looks like we'll get sine of theta is equal to a half. Sine of theta equals to a half. This would be the first solution I could have where sine of theta is equal to 1/2. I consider 30, 60, 90 triangle. Yep. Kevin, you got that? Yeah, sine of 30 degrees would give us 1/2. So 30 degrees in radians, we would say is pi over 6. So pi over 6 is one solution. And what would be a second solution that we would get for positive 1/2?
5 pi over 6.
5 pi over 6, right? The second quadrant solution. Same reference, it would give us 5 pi over 6. So we have two solutions for that. And we also have two solutions for the cosine of theta equals 0. So if we put all these solutions together, we can say here on the side, theta is equal to pi halves, 3 pi halves, pi over 6, and then 5 pi over 6. There we would be done. We're just going to be finding solutions in the 0 to 2 pi range. Excellent work. Is there any questions from this double angle equation that you guys like to ask? Okay, so we'll keep rolling through. We'll have another double angle equation of C that we'd like to attack. All right, so we have cosine of 2 theta minus 3 sine theta minus 2 equals 0. So just in terms of strategy of looking at this, when I see multiple trig functions, like a sine and a cosine, there's really two ways to go about it. In some way, I'd like to either separate these two things, or I'd like to just convert the equation in terms of sine or cosine only. So usually it doesn't help to have multiple trig functions when we factor. So let's consider how we might represent this left side in terms of only sine or only cosine. We know that there is a few identities for the cosine 2 theta, and that might be helpful in this case as well. So what would be a representation of cosine 2 theta that involves sine? So we can turn this into a equation of sine. Yeah, I think you can use that for sure. This could be represented as 1 minus 2 sine squared theta. So that is our cosine 2 theta representation. That would be in terms of only sine. I think that would be definitely helpful. And so we have that, and then we need to subtract 2 for the 3 sine, and the minus 2 equal to 0. Okay, so now it looks like we're all in terms of sine, and it looks like we might have a quadratic form. So we want to consider some techniques that we used in that last section with a quadratic. So let's consider that. So first, we might want to think about kind of moving everything into its proper position. We do have some constant terms that we could add together. And then I'll also consider trying to make that leading coefficient a positive solution. So we could first rewrite this as negative 2 sine squared theta minus 3 sine. And then 1 and negative 2 are going to give me a negative 1 equal to 0. And just to make this a little prettier and easier to work with, notice that all the coefficients here are negative. So one way I can sidestep that is just multiply both sides by negative 1. If I multiply both sides of this equation by negative 1, I can turn all of those coefficients positive, and it'll still be equal to 0, because 0 times negative 1 is still 0. So I'm just going to represent this as 2 sine squared theta plus 3 sine theta, and then plus 1 equal to 0. All right, so I think we're now in line to be able to think about whether this factors or we're going to have to use another technique such as a quadratic formula. So what are the ways that you guys see this factoring, if possible? I separated this into 2 factors. This doesn't have necessarily a lot of options to factor, which is nice. If I looked at the leading term, 2 sine squared, there's only one way that that can separate. So that would be 2 sine theta and just sine of theta to get that product. And then to be able to get a product of 1, that plus 1, we can only separate that as plus 1 and plus 1. So that factoring really has only one way to work. So 2 sine theta plus 1 and sine of theta plus 1 should get us what we need. If you wanted to double check our cross term here, 1 times sine theta is just 1 times, or it's just sine theta. And then we'd have a second cross term of 2 sine theta, which would give us 3. So that, in fact, is a proper factoring of that quadratic in terms of sine. And so now we have 2 factors to look at and set equal to 0. if I set this first factor equal to 0, we have 2 sine theta plus 1 equal to 0. And we'll, again, just rearrange that and see if we can solve for sine. So we have 2 sine equals -1, or sine of theta equals -1/2. And if I wanted to consider where the sine function is going to be -1/2, let's consider that together here. What would be the first angle that we would find that gives us a -1/2 for sine?
Is it 2 pi over 3?
2 pi over 3? I think that might be close. So usually, so the first, I guess, the reference angle to get positive, sine of pi over 6 is going to give us positive 1/2. So we're going to have something with a denominator of 6. I think you got that, Anya. 7 pi over 6. Yeah. So a third quadrant. Going to be one solution, 7 pi over 6. We note that one. And then I think we'll get a fourth quadrant solution where sine is negative. What would be the fourth quadrant solution?
11 pi over 6.
Yeah, 11 pi over 6. Excellent. So we'd have another one. And this one would be 11 pi over 6. So we have two solutions there. 7 pi over 6 and 11 pi over 6. Let's take a look at the right side, or not the right side, but the second equation. We have sine theta plus 1 equals 0. We'll see if we can find a solution for that as well. So this means sine of theta equals -1. So what is the angle that will give us -1 for sine? Yep, that would be 3 pi over 2, Anya. That's very good. So on our unit circle, 3 pi over 2 would be the only solution where sine is equal to -1. So that's going to give us 3 total solutions for this equation. So here theta is going to be equal to 7 pi over 6. We'll have 11 over 6 and 3 pi over 6. So, or 3 pi over 2, excuse me. Pi over 2. There we go. So 3 solutions theta radians there. All right, so let's pause here for a moment, see if we have any other questions. I know this is coming at you guys kind of quickly, so try to give you a chance to view this and pick out any questions that you guys might have at the moment. Okay, so these are just a couple additional techniques here. We're using that double angle formula to help us, and then the factoring technique again. Okay. So let's consider another equation quadratic form, and this is going to have kind of a different result we're necessarily used to seeing, but I do want to expose you to this possibility. I don't necessarily know if this is super common in the homework, but it could happen. So if we wanted to consider this equation, we have 2 cosine squared theta minus 4 sine theta minus 5 equals 0. So another kind of quadratic form. And again, cosine squared theta, we can again put in terms of sine. So we're going to start really similar to what we did in our last problem with the cosine 2 theta. But in this case, we're going to use a different identity, and that identity involves the Pythagorean theorem. So remember that we have that sine squared theta plus cosine squared theta equals 1. That was our Pythagorean theorem for trigonometry. So in this equation, instead of cosine squared theta, we could actually represent this as 1 minus sine squared theta by rearranging that. So cosine squared theta here is 1 minus sine squared theta by subtracting the sine squared. So here we're going to be able to just manipulate this in terms of just sine. All right, so if we kind of continue further, we can distribute that 2 and then rearrange and try to add like terms as we go. So we'd have 2 minus 2 sine squared theta minus 4 sine theta, and minus 5 equals to 0. All right, and again, we have like terms that we could add with those constants. We'll do that. So that would be minus 5 and plus 2 would be minus 3. And then last but not least, we can do another, again, the technique of multiplying by -1 to clean this up a bit. So if I multiply by a -1 on both sides, I can kind of make this equation a little bit prettier with all positive coefficients. Okay. All right, and now we'd want to consider, can this factor, are we going to need a different technique? And in this case, we will need a different technique other than factoring. If we consider, the factoring technique, factoring actually doesn't work here because we don't get the right cross term when we have products of 3 and 2. So as much as you want to factor this one actually doesn't factor well. So we want to consider now a quadratic formula. So just to remind ourselves of a quadratic formula, we can consider if we set, say, x equal to sine of theta, just to kind of simplify the equation part, we could say that this is 2x squared plus 4x plus 3. This is the quadratic I'm actually wanting to solve. And in terms of the quadratic formula that we would want to put together, I would have x is going to equal to the quadratic formula, which is -b plus or minus square root of b squared minus 4ac all over 2a. And for this purpose, I'm going to just center in on that square root for just a moment. And just, this would be probably to do the full equation, is I want to just double check that this square root is going to give me a real number solution. So I'm going to consider kind of this portion equation just for right now. And I want to make sure that that square root actually gives me a positive number inside. So if I consider that section there, square root of b squared, what is the b value in this equation? The b value in that equation is a 4, right? So this is our b, so this is our c, and that's our a. So we have 4 squared minus 4 times a is 2, and then the c is 3. So if we consider that equation, or at least the expression here, we have 16 and then minus, looks like 4 times 2 times 3 is going to give us 24, which is going to give us the root of -8. Now, the minute we see this, should kind of throw up red flags in our mind. This is not a real solution here, square root of -8. Therefore, this equation at large is not going to have real number solutions for theta. So right away here, by testing this little discriminant, it's called, the square root here, we would say that this is going to have no real solutions. And I would just actually stop my solving process here with no real solutions in this case, because we do get a discriminant that's negative. So this will not produce any real solutions, and we would just stop the solving process there. So again, it's probably not going to happen often, if at all. I'm not sure if the homework actually gives you something like this, but I did want to expose you to that in terms of kind of the solving process with the quadratic formula a little bit. So again, let me pause for questions here with this problem, if you guys have any. Could you maybe rephrase that question? I'm not exactly sure what you're getting at. Yes. So yeah. So if you get an imaginary solution like that, then we would just consider no solutions, and you could stop the solving process. That's correct. Again, I'm not sure if it's going to happen all that much, if at all, but just in case, you'd have that ready for you. All right, I think we have one more problem to take a look at, and it involves a half angle. And so we'll try to walk through this with the rest of the time that we have with part E. All right, so in terms of a half angle, we want to consider how we could use a half angle using our half angle formula if we can. So we have a sine of theta over 2 minus cosine theta equals 0. All right, so one way we could solve this is to just consider what is sine of theta over 2 representing. Well, let's start with that. If you look at our half angle identities, one way I can represent sine of theta over 2 is the following. I could say that this is equal to the square root of 1 minus cosine theta divided by 2. Okay, so that would be kind of our half angle identity, one of them at least. And really, technically, there is two cases here. There could be a plus and minus outside. But for the purpose of this problem, we can actually just play with and work with the positive version of that root. And I'll show you guys why in just a minute. I'll just leave it there for right now, equal to 0. This does look a little complex, but there is a couple steps that we can use to simplify this pretty quickly. If I considered separating these are all in cosine now, which is nice. But I do want to separate this and somehow get rid of that square root. So one thing I could do here is add cosine of theta to both sides. And so I'd have the plus and minus root over 2 equal to cosine. And at this time, this is kind of why we don't necessarily need that plus and minus, is because we can square both sides of this equation to get rid of that square root. And really the plus and minus is not necessarily going to matter on the outside. So if I consider square both sides here, that plus and minus doesn't matter, because if we square positive, it's going to be positive. Square negative, it's going to be that same positive value. So in this case, we have just the stuff that's inside, 1 minus cosine theta over 2. And then we'll have cosine squared theta. All right. What do you guys see as the next thing that we could do? We only have a few minutes left here, but we can finish this up. What's the next operation we could work with there? Multiply by 2 on both sides. Multiply by 2. So we get 1 minus cosine theta equal to 2 cosine squared theta. Okay. What could we do next? I don't think we necessarily need to involve the sine function. We do have a cosine squared and a cosine. So we can think about this as another quadratic. If I subtract 1 cosine to both sides, I will have a quadratic set equal to 0. Yeah. So I could say 2 cosine squared theta plus cosine theta minus 1 is set equal to 0. So we have another quadratic form that we could work with, try to factor here. And in this case, this does factor. We're running a little short on time. I'll try to finish this up for you guys. If we factor this out, we'll have a cosine term. And we'll also have a cosine term to get that first position taken care of. And then we'll have a -1 and a +1 to get that -1 product. So there's, again, two equations that we'd like to solve for there. So the first one is just going to be solving 2 cosine theta minus 1 equal to 0. If we rearrange this, we'll just get a half, so 1/2. And we've seen this actually a couple times before in the class. The cosine theta is going to be 1/2 in 2 positions. That's at 60 degrees and 240. So that would end up being pi over 3, pi over 3 for 1, and a 5 pi over 3 for a second. That would be 300 degrees and 60 degrees. So those are 2 solutions there. This one gets is a little tricky because again we want to kind of double check our solutions. If we did our cosine plus 1 equals 0, that would be a cosine theta equals -1. What would the angle be there to solve for cosine theta equals -1? Or does our x coordinate equal -1? That would be pi, right, Aiden? So we'd have theta equals pi. Okay. Again, whenever we're working with these half angles, it's a good idea to check our solutions. In this prime example, y. If I wanted to check, I'll specifically check this last solution because this is the one that causes a problem. If I check that if theta is equal to pi is a valid solution, I would say that sine of, we have pi over 2 minus cosine of pi. I want to verify that that's actually 0. But if I take a look at that, we just said if we have the sine of pi over 2, or sine of 90 degrees, that's going to give us 1. And then we'll minus cosine of theta. Well, cosine of theta, we just said was -1. 1. Cosine of theta is -1. And this, in fact, actually gives us 2 instead of 0. So this actually is not a solution. This is what we would call an extraneous solution. And would not actually be a valid solution for the equation. The other 2 will be valid solutions if you double check those in the equation. So these are true solutions. But the theta equal to pi here is going to be an extraneous solution, which we would not include in our solution set. So specifically when we're working with half angles, make sure that you are careful with those. All right, so I'm a little over time today, but again, if you guys want to stick around for another 20 minutes or so, I'm happy to answer some more questions. So tomorrow you guys have some 6.3 to work on, I believe some 7.1, and then we will meet again later this week to work on some more chapter 7.